So, welcome to the 24th lecture. So, today we are going to study closure properties of context free languages. So, the first closure property that we will see is union. So, and the context free languages are closed under union, which means that if L1 is a context free language and L2 is a context free language, then L1 union L2 is also a context free language. So, the proof is not very difficult. So, let us say that L1 is a context free language via a context free grammar G, let us say G1 equals V1 sigma P1 S1, okay, and L2 is a context free language via a context free grammar G2, which is V2 sigma P2 S2. So, using these two we will construct a grammar G, which I will call V sigma P S, such that language of G will be equal to L1 union L2. So, how do we construct this grammar? So, the thing is that, so the variables will just be the union of these two. So, we will just assume that the symbols that we use for the variables of G1 and G2 are different. Okay. So, this is just for so that we do not mix. So, A used here should not be the same as an A used here. So, we can give them separate names, but basically what we will have is V will be equal to V1 union V2. Production rules also, P will be equal to P1 union P2. Now, we have a variable S. Okay. So, actually what is this variable S? So, this is a new variable that I add to V. Okay. So, this is a variable, a new variable that I add, and in the production rule I will have another rule, okay, which takes S to S1 or S2. Okay. So, this is generating all strings that are generated by S1 or all strings that are generated by S2. Okay. So, this is why it accepts the union. So, this is the main construction. Similarly, if we have concatenation, how do we do? So, the entire construction remains the same. So, again we take the variables as the union of the two variable set, the productions as the union of the two production sets, and we have a new start variable S, but this time we have the additional rule. So, we will have an additional rule of the form S going to, let me write this as S going to S1 S2. So, it generates a string generated by S1. So, it generates a string over the language L1 first, and then concatenates it with a string generated over the language L2. Okay. So, this will generate by this construction L of G will be L1 concatenated with L2. The next operation that we will see is the star operation. Again, in the case of star operation, we only have a single grammar. Okay. So, let us say we have a single grammar G1, which is the grammar for L1, and I want to construct a grammar for L1 star. Okay. So, I have a grammar where I have a new production, I have a new variable S, and I have a new rule S going to S1 S. Okay. And by this language of G will be language of L1 star. Okay. So, this is for star. So, these are the three basic closure properties, and we have seen that regular languages are also closed under these three properties, but there are other closure properties as well. For example, intersection, complement, reversal, homomorphism, inverse homomorphism, and so on. So, let us look at some of those properties. So, and see what happens when we try to study the closure properties of context free languages under these properties. So, what about reversal? Okay. So, suppose, so again context free languages are closed under reversal. And the idea is, suppose I have a rule of the form some A goes to A1, A2 up to some AK, then replace it with the rule A going to AK dot 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 A2 A1. Okay. So, basically look at the right hand side of every production rule and reverse it. Okay. So, whatever string is being generated by A will get reversed. Okay. And by this construction we get a new grammar. Let us say from a grammar G I get another grammar G prime. So, L of G prime will be the reverse of the language of G. Okay. So, let us say this was grammar G and this is a grammar G prime, then L of G prime is reverse of L of G. Okay. So, similarly under homomorphism and inverse homomorphism also context free languages are closed. So, context free languages are closed under homomorphisms and inverse homomorphisms. Okay. So, for homomorphism actually we can start with a context free grammar for the language and construct a context free grammar for the homomorphism of that language. And for inverse homomorphism we can actually do it using push down automaton. Okay. So, in our last lecture we saw that push down automaton and context free grammars both have equal expressive power. In other words, even push down automaton accept the same class of languages as context free languages. So, to prove inverse homomorphism we take a language, we assume a push down automaton for that language, and then using that we construct a push down automaton for the inverse homomorphism of that language. So, I will not give the proof of this thing, I will just leave that, you should try that as an exercise, but let us just remember this as a fact. Okay. So, now what about intersection? Okay. So, for intersection there are two things. So, we can study two properties or two intersection properties of context free languages. Okay. So, one is of course, if I have a language L1 which is context free and I have a language L2 which is context free, what happens to L1 union L2? Okay. Also, I can study the following: if I have a language L1 which is context free and I have a language which is L2, a language which is regular, then what happens to the intersection of these two languages? So, intersection of regular with context free and of course, context free with context free. So, we will study both these. So, if L1 is a context free language and L2 is regular, then L1 intersection L2 is a context free language. Okay. So, let us try to show this, or in fact, even if I, before giving the construction, the idea is the following. So, suppose I have a PDA for L1. Okay. So, suppose there is a PDA n for L1 which has states, let us say Q1, sigma, gamma, delta, let us call it Qn instead of 1, delta n, S n and F n. Okay, so, this is a push down automata for L1, and because L2 is regular, I can assume a DFA for L2. Okay. So, let us say there is a DFA for L2, M which is equal to Qm sigma delta m S m F m. Okay. So, this guy is a PDA and this guy is a DFA. So, what we will do is we will construct the product automaton of M and N. Okay. So, essentially the product automaton is the following. So, I look at the cross product of Qn and Qm. Okay. So, all tuples where one pair where one element comes from Qn and the other element comes from Qm, and that is going to be my set of states of the product automaton, and from there I will make transitions simultaneously according to n and m. So, the first element of that pair will make a transition according to Qn, and the second element of the pair will make a transition according to delta m. So, the first will make according to delta n, second will make according to delta m. Okay. So, that is how it goes, and in the end I will check if both n and m accepts, then I will basically accept. So, now comes the question of the stack. Because I need to prove that L1 union intersection L2 is a context free language, it is sufficient for me to construct a push down automata for L1 intersection L2. Okay. And in the push down automata, I am allowed a stack. So, I will use the stack of the push down automata to simulate the stack of n. Okay. So, I have this additional stack that is given to me. So, I have this is my m. So, I create a cross product with n who has this stack s given to it. So, what I do is I will create an automata, let us call it n prime, and I will use the stack of n prime to simulate the stack of s. Okay. So, the formal description is as follows. So, we construct n prime which is equal to q sigma gamma delta s and f, where q is the cross product of Qn and Qm, S is basically the pair S n comma S m. So, I take the start state of both these. What about F? When do I accept? So, I basically accept if both delta n and delta m make a string accept. Okay. So, basically I will take the cross product of Fn and Fm. Okay. So, both states must I look at all those pairs A comma B where A is an accept state and B is an accept state of n and m respectively. Now, what about delta? So, I say that so note that this is a PDA. So, I say that some P comma Q comma Y is an element of delta of R comma S comma A comma X if. Okay. So, suppose if I am at a state R comma S, I read a symbol A on the tape and the top of the stack contains X, then I will go to the pair P comma Q and replace X with Y if the following happens. If first of all the first transition is according to the transition of the PDA, that is P comma Y belongs to delta n of R comma A comma X. Okay. So, this transition is according to the PDA, and second is Q equals delta m of S comma A. Okay. So, recall that delta m is a transition function of a DFA, therefore, this should be on the state S. So, this S and this S are not the same. So, let me instead of S, let me give this a different name. So, let me call it R comma T. Okay. So, R comma T, and here also I will write as T. Okay. So, from state T on input A, the DFA goes to state Q. Okay. But now, because this is a PDA, A can be the epsilon symbol also. So, T equals Q if A is epsilon. So, if A is epsilon, then basically Q is defined to be equal to T. Okay. So, this is the construction. So, now what about intersection of two context free languages? Okay. So, let us look at two languages, L1 which is A to the power n, B to the power n, C to the power m, where n comma m are is greater than 0. Okay. So, this is one language, and another language A to the power n, B to the power m, C to the power m, where once again n and m are greater than 0. So, in the first language the number of A's is equal to the number of B's, C can be arbitrary. In the second language the number of B's is equal to the number of C's, A can be arbitrary. Okay. So, you can easily show that L1 and L2 are context free language. In fact, I can give a context free grammar for L. Okay. So, for L I can give a following grammar. So, I have S which generates strings of the form S1C. So, S1 will generate all strings of the form A S1B or epsilon, and C will generate strings of the form small c, capital C or epsilon. Okay. So, the first part generates all strings that have equal number of A's and B's, and C generates some arbitrary number of C's. Okay. So, this generates the language L1. Similarly, you can construct a grammar which generates the language L2. Okay. So, this proves that L1 and L2 are context free. Now, what about L1 intersection L2? What is this language? So, if you look at this language, so this language contains all those strings that have A's followed by B's followed by C's, where the number of A's must be equal to the number of B's, okay, because they are strings in L1, and the number of B's must be equal to the number of C's, because they are strings in L2 as well, which implies that A's, B's and C's must be the same number. Okay. So, it has strings of the form A to the power n, B to the power n, C to the power n, okay, which we have already shown, which we have already seen is not a context free language. Okay. So, therefore, context free languages are not closed under intersection. Okay. What about complement? So, if we want to study complement, okay, so I can write A intersection B as A complement union B complement whole complement using De Morgan's law. So, if context free languages were closed under complement, then if A and B are context free languages, A complement would be a context free language, B complement would be a context free language. We just saw today that union of two context free languages is a context free language. So, A complement union B complement is a context free language, and again we take whole complement of a context free language. Hence, the right hand side is a context free language, but we just proved that intersection of two context free languages is not necessarily a context free language. Hence, complement is context free languages are not closed under complement. Okay. Okay. So, similarly, also under set difference. Okay. So, now let us look at an application of these closure properties. Okay. So, we have seen several closure properties so far. So, let us quickly look at an application. So, suppose I consider the language L equals A to the power n, B to the power n, A to the power 2m, B to the power 2m, where n comma m are greater than or equal to 0. How can we prove that this language is a context free language without constricting a grammar for it using closure properties? Okay. So, we will use the fact that A to the power n, B to the power n, let us give this a language a name, let us call this L1, is a context free language. Okay. Now, consider the homomorphism, okay, H, which takes A to AA and B to BB. Okay. what does H do to the language L1? Okay. So, it takes, if I have a string of the form a to the power n b to the power n, it will take that string to a to the power 2n b to the power 2n. Okay. So, it creates, it has all strings of the form a to the power 2n b to the power 2n. Okay. So, even number of a's and even number of b's. So, it has a to the power 2n b to the power 2n for n greater than or equal to 0. Now, observe that the language L that we started off in the beginning is nothing but concatenation of L1 with H of L1. Okay. So, L basically has all strings which have a part which is a to the power n b to the power n and another part which is a to the power 2m b to the power 2m. Okay. So, it takes some string from L1 and it takes some string from H of L1 and it produces a string in L. Okay. So, because regular context free languages are closed under homomorphism and concatenation, therefore, L is a context free language. Okay. So, I will stop here. Thank you.